Okay, imagine stepping into an environment of absolute, total darkness.
Right. Pitch black.
You can't see a thing, can't sense heat, the air's still. Now, picture trying to locate something tiny, like a vole.
Making just the faintest noise
Yeah.
yards away.
Exactly, and then striking it with pinpoint accuracy.
Yeah.
How? When you literally cannot see.
Well, that's why we're diving deep into Tyto alba, the barn owl. Because its hunting method is, I mean, it's just one of the marvels of biological acoustics.
It's more than just listening, isn't it?
Oh, absolutely. It navigates, it calculates, it even corrects its flight path, all using just sound.
So for this deep dive, we're leaning heavily on some classic research, mainly work by Masakazu Kanishi.
Yeah, he did incredibly detailed work, building on earlier observations from people like Payne and Drury.
Yeah.
Really quantified things.
And our mission today, yours and mine, is to get beyond just saying, oh, the owl uses sound. We want to really understand the sensory details.
The acoustic engineering almost.
Exactly. What makes this owl this silent, zero visibility predator?
Okay, let's unpack it. I think we have to start with the end result, right? The strike itself.
Okay.
So when an owl decides to go for it, in total darkness, its flight is fast.
Yeah.
We're talking 3.6 to 4 meters per second.
Which is, what, almost 9 miles an hour in the dark?
Pretty quick. But then as it gets close, maybe within, say, 60 centimeters.
About 2 feet.
Yeah, roughly. The whole flight posture changes. It's quite dramatic.
How so?
Well, it pitches forward, brings those heavy feet up,
Talons out.
talons out, spreading this oval pattern. Ready?
Yeah.
And here's the kicker. Often, right before impact, it closes its eyes.
Closes its eyes, so it's flying blind at the very last second.
Totally reliant on the acoustic picture it built just moments before. It's calculated.
And we know for sure it's only acoustic because of that one famous experiment, right?
The paper test. Yeah, that's definitive.
Can you walk us through that one?
Sure. So they had a mouse walking quietly across the floor. Simple enough.
Right.
But it was towing a little piece of rustling paper, a few inches behind its tail.
Okay, and the owl?
The owl didn't strike the mouse. It ignored the actual animal.
It went for the paper.
It struck the paper. Every time.
Wow, so that just seals it. It's not sight, obviously. It's not smell.
And definitely not sensing body heat. You know, infrared, none of that. The rustling sound was the only thing it needed.
That one result really tells the whole story, doesn't it?
It really does. And it explains why it can close its eyes at the end, if the target location is locked in by sound and the flight path is set.
It's like launching a tiny feathered missile based on the last known coordinates.
Exactly. It's essentially ballistic at that point.
Still feels risky, though, compared to, say, using your eyes the whole way.
It is, potentially. But the risk is offset by how incredibly precise this acoustic system is, which we'll get into.
Okay.
But another important point the research makes is that the owl isn't stupid. It doesn't just attack any noise it hears.
Ah, right. It learns to filter.
Exactly. It learns very quickly to tell the difference between sounds that mean food
Like vole rustling.
and sounds that mean danger or not food. It discriminates. This ability to sort sounds is just as vital as being able to locate them.
Okay, so it filters out the noise.
Yeah.
But to filter, it needs to know what signal it's actually listening for. What is that vole sound signature?
Right. So researchers looked at the actual noises voles make when they rustle around. They used spectrographic analysis.
That's like a visual map of sound frequencies?
Pretty much. And they found those rustles contain, well, a really broad range of frequencies. It's not just one simple tone.
Okay, so the prey makes lots of sounds.
Mm-hmm.
What can the owl actually hear? How does its hearing compare to ours, for instance?
Well, if you look at the audibility curve, the graph of what it can hear, the barn owl is way more sensitive than humans, between about 500 hertz and 10 kilohertz. That's a big chunk of the mid-range.
More sensitive than us. What about cats? They're hunters, too.
Good point. It's pretty similar in sensitivity to a cat, up to around 7 kilohertz.
But what happens after 7 kilohertz?
That's where it gets interesting. The owl's sensitivity just drops off sharply. And above 12 kilohertz, believe it or not, we can actually hear better than the owl.
Huh. So it's really specialized in that lower to mid-high range.
Hyper-optimized, you could say. Its auditory world is tuned differently.
Okay, so now we know what frequencies it can hear well, but that doesn't automatically mean those are the frequencies it uses for hunting, right?
Exactly. That's the crucial distinction. Hearing something is one thing. Using it to build a precise 3D map in your head is another challenge entirely.
Right. We humans, we sort of solve the location problem differently based on frequency, don't we?
We do. For low frequencies, where the sound waves are long compared to the distance between our ears.
We compare the timing. the phase difference.
Right, which wave peak hits which ear first. But for high frequencies, the waves are shorter, and our head casts a sound shadow.
So one ear hears it louder than the other. Intensity difference.
Exactly. And for us, there's that awkward range, maybe 2 to 4 kilohertz, where neither method works that well. The wavelength is just wrong for our head size.
The acoustic hump.
Right. Now, the owl,
Yeah.
it seems to solve this problem in a really elegant way.
Huh.
It basically just ignores the low-frequency phase method for the most part.
It just bypasses that whole tricky bit.
It seems so. Experiments showed it's actually pretty poor at locating low-frequency tones, like, say, 3 kilohertz.
Okay, so if not low frequencies, then what?
Its sweet spot, its optimal range for location, is incredibly specific. Pure tones between 6 and 9 kilohertz were the easiest for it to pinpoint accurately.
6 to 9 kilohertz, that's quite high-pitched.
It is. But even a pure tone isn't ideal. Think about it. A single frequency doesn't give you quite enough information for superfine accuracy.
Right, real-world sounds aren't usually pure tones, they're messy.
Exactly. And the owl thrives on a bit of that messiness. The most accurate location wasn't with a pure tone at all.
What was it then?
It was using a band of noise, specifically a 4 kilohertz wide band centered around 7.5 kilohertz.
So like all the frequencies between 5.5 and 9.5 kilohertz?
Precisely. That specific slice of the rustling sound spectrum contains everything the owl needs for an accurate fix.
It's like it's a living filter, tuning into just that narrow critical band and ignoring everything else.
That's a great way to put it. It finds that sonic sweet spot. It doesn't need more frequencies. It just needs the right frequencies in that specific band.
That's the minimal information for a kill in the dark. Incredible.
It really is efficient.
Okay, so we know the signal it targets that 5.5 to 9.5 kilohertz noise band. But how does it turn slight differences in loudness at each ear into a precise 3D target location? This must involve the head shape, right?
Absolutely. And this is where it gets, I think, really fascinating. It's about the physical structure, specifically the asymmetry of the ears.
Asymmetry, so they're not lined up.
Not quite.
Oh.
Most animals, including us, have pretty symmetrical ears. Good for figuring out left-right position, the azimuth. But the barn owl, its ears are physically lopsided. The openings aren't level.
Wait, really? Like one's higher than the other?
Exactly. The opening for the left ear canal is noticeably higher on the skull than the opening for the right ear. And the skin flap around the right ear is also positioned lower.
And this isn't just random variation.
Nope. It's a consistent feature across barn owls. It's part of the design. The structural imperfection is actually the functional solution.
Wow. How did they prove that this asymmetry is what lets it judge height or elevation?
A really simple but clever experiment.
Yep.
Earplugs.
Okay.
They gently plugged one ear at a time. When they plugged the owl's right ear, the lower one,
Yeah.
the owl consistently struck short of the target. It undershot vertically.
Okay. And the left ear plug?
When they plugged the left ear, the higher one, it consistently landed slightly beyond the target. It overshot vertically.
That's direct proof. So the vertical difference between the ears lets it use intensity differences
In that crucial 6 to 9 kilohertz range.
to figure out not just left, right, but also up, down, the elevation.
Exactly. Time differences between the ears would be incredibly tiny and hard to use for elevation with such a small head. But the intensity difference, amplified by the asymmetry, gives it that vertical coordinate.
That is just biologically elegant. A 3D acoustic map from uneven ears.
It really is.
And of course, we can't talk about the owl's head without mentioning that iconic face, right? The heart shape.
The facial disc, yeah, absolutely essential. It's not just for looks.
What does it actually do?
It's basically a sound collector. It's made of this curved wall of really dense, stiff feathers.
Like a little satellite dish on its face?
That's a perfect analogy. It acts like a biological parabolic reflector, gathering those faint rustling sounds and funneling them towards those asymmetrical ear openings.
And I bet they tested its importance, too.
Oh, definitely. They carefully removed those facial rough feathers.
And what happened?
The owl's hunting accuracy just plummeted. It made huge errors.
But could it compensate?
Yes, but only if they cranked up the volume of the sound source. They found that increasing the sound level by about 10 decibels restored the owl's accuracy.
So the disc itself provides about a 10 dBB boost, like a built-in amplifier.
Exactly. Which matches theoretical calculations for a disc that size, around 7 centimeters. It helps it hear those incredibly faint sounds and contributes to the directional information.
Amplification and directionality. Wow, okay, so we've got the static picture, but prey moves. How does the owl handle that? Can it adjust mid-flight?
It absolutely can. The researchers called them moonshots, these mid-flight course corrections. It's not just point and shoot,
It needs constant updates then.
pretty much. They found accuracy dropped way off if the sound stopped the moment the owl took off. It needs that continuous or at least intermittent feedback.
How quickly could it retarget if the sound came back on?
Amazingly fast. Even if the sound came back on, say, half a second into a 1.2-second flight, it could still adjust and hit the target successfully.
But if it was silent for too long?
Right. If like 80% of the flight was silent, the accuracy was lost, it needs to track in something close to real time.
And what happens visually, or rather physically, when the target moves during flight? Like if the sound jumped from one speaker to another?
That revealed something really interesting. The owl would actually slow down its flight speed. Sometimes it would even hover for a split second.
Okay. Pausing to recalculate.
Seems like it.
Yeah.
And crucially, it would snap its face, its head, towards the new sound location first.
Before turning its body.
Yes. The head leads, locking onto the new acoustic target. Then the body follows, correcting the flight path. Head first, then body.
Fascinating. It really shows the head and the disc as the primary targeting system.
Definitely.
Now, the final piece. How does it do all this delicate listening and correcting while flapping its own wings? Wouldn't its own flight noise drown out those faint prey sounds?
That's the other side of the acoustic coin, the sheer silence of its flight.
We know barn owls are silent flyers, but how does that work with the frequencies?
The physics of it is perfectly matched to its hearing strategy. When you analyze the sound of a barn owl flying, it almost entirely lacks high-frequency components.
So no whooshing or whistling sounds like other birds.
Very little. Almost all the sound energy from its wings is concentrated below 1 kilohertz. Really low frequency.
And the sounds it needs to hear from the prey are?
Up in that 6 to 9 kilohertz range.
So its own flight noise is in a completely different frequency band. They don't interfere.
Exactly. The sound it makes doesn't mask the sound it needs to listen for. It's the ultimate evolutionary synergy.
That is incredible. Talk about specialized design.
And there's a bonus layer of stealth, too.
Oh, yeah.
Most small rodents, like the voles and mice it hunts, actually have pretty poor hearing below about 3 kilohertz.
So they literally can't hear the owl coming.
For the most part, yes. The owl's low-frequency flight noise is below their hearing threshold. Total acoustic camouflage. Though some desert rodents like kangaroo rats can hear low frequencies, but they aren't typical barn owl prey everywhere.
Wow. Okay, so putting it all together for you, the listener, what's the big picture here?
Well, you've seen how the barn owl is this biological acoustic marvel, right?
Mm-hmm.
It relies almost entirely on that very specific narrow band of high-frequency noise, 5.5 to 9.5 kilohertz.
Which is amplified by that amazing facial disc.
And then spatially mapped in 3 dimensions by those vertically offset asymmetrical ears using intensity differences.
Allowing it to make incredibly rapid mid-flight corrections to hit moving targets in total darkness.
Oh, while flying so silently in the crucial frequencies that its prey can't hear it and its own noise doesn't interfere with its hearing.
It's just a perfect system, it seems. Finding the maximum necessary information, that 3D map, from the minimum possible input, just that narrow sound band.
It's incredibly efficient.
But thinking about the sources, a lot of this relies on lab work, right? Controlled conditions, electronic signals from speakers.
That's a really important point. These experiments are brilliant for isolating variables, but they use simplified signals.
Which raises a final question, doesn't it? How much more is there to the story in the wild?
Exactly. How much of the barn owl's full potential are we missing? There are hints, for example, that they might subtly change the shape of their facial disc actively.
To fine-tune the focus, maybe?
Perhaps, or maybe they integrate other subtle cues in a noisy, complex natural environment that we just can't replicate easily in the lab.
So the provocative thought for you to ponder is this. What aspects of this owl's true acoustic genius, its ability to handle real-world noise and perhaps even manipulate its own sensory equipment, are still waiting to be discovered out there in the field?